let's take a look. Let's take a look at the book stuff here real quick from a few days back. So here we did number 1 in class together. Number 2, you're supposed to do some midpoint rectangles. So, you know, thinking about, again, our next quiz, which will be a while, actually, as we kind of mix in review days and with a short week next week. And so it's probably going to be the week after next, somewhere in there, as we finish up those things. Depends how much we get done on that next full week, so it might be towards the end of that week. But anyway, so we have this region in here, so the area between these two curves. So we were talking about how to do this area, you would think of a strip. If we were just actually doing the actual area, you would think of a strip in here, and you would think of this area being the adding up of all of those little strips of area. The integral does the adding, okay? The integral, this is the adder right here, right? That's what adds this up. And then it's just got to be the width of that strip, which is your dx, and then the height of that strip, which is simply that, what is that, sine graph on this one? Is that sine, and what's this one, cosine? Is that what it was? Okay, so it's simply going to be this y value, which is sine, because that graph says y equals sine, so the y value of this graph is sine x, and the y value of this graph is cosine x, and so it's simply going to be sine x minus cosine x, right, all the way through. The y's are all sine, the bottom y values are all, the top y values are all sine x, and the bottom y values are all cosine x. You subtract those, you get the height of that strip, you multiply that by the width of that strip, or the dx, and let the integral add those up from 1 to 3, you've got the area of that region. That's the idea. That's this top minus bottom idea. Now we're going to find out over the next couple of days, or the next couple of weeks, I guess, we get farther in chapter 7, this idea of this strip becomes really important, this idea of top minus bottom, or if it's horizontal, the idea of right minus left. Okay, so anyway, you were supposed to do some midpoint rectangles, so thinking about, you know, height of a rectangle. So again, not a huge deal. Not going to do much of that next quiz, probably at all. But that's where this idea of the height of the rectangle comes from, because we think of filling this space with rectangles. Okay, so I just used F and G, but again, your width is 0.2, and so you start at 1. So your width is 0.4, excuse me. So your first midpoint would be at 1.2, and then at 1.6. So forth, so on. Okay. All right, number 3. So we had left off talking about number 3, and you were just supposed to find this region, you're supposed to find this region, and then supposed to find the area of this region using vertical strips. Okay. So this would simply be the integral here from 0 to 1 of the top curve, which is 1, minus this. Now what did we do? We had to solve that, right? So we had y equals plus or minus square root of 1 minus x. Was that right? Is that what we had on that one? Okay, and so this is the top part of that, so that would just be square root 1 minus x. So that would be this region. This is the one that's sometimes tricky, this region down here. This is, again, from 0 to 1, because these strips would fill this space from 0 to 1, okay? And it'd be the top curve, which is negative root 1 minus x, and then minus the bottom, which is negative 1, right? This is the y value of negative 1, which would turn into that. Well, now when you look at that, look what happens once you get done with that. It is actually the same as this, isn't it? It actually is the same region, and because of symmetry, to be honest with you, because of symmetry, we know that this area is going to be the same as that area. So if you were really doing this on an AP test or free response question or something, it would be perfectly valid to do this region and then double it. Because of symmetry, you would know those regions be the same. Okay, unless it actually said set up an integral for each of the 3 regions, you know, then you would want to do that. This region is just a triangle, so you could actually use geometry. But if, again, they said set up an integral, the strips would fill the space from 1 to 3, and then you would have top y value 1 minus bottom y value, which would be x minus 2. The y value here would be x minus 2. Now make sure you do that. I'm fine if you leave it like that. You certainly can simplify that. But those should be your 3 regions. You add those up, just type them into your calculator. I think they were supposed to add up to 8/3, if I remember right. Okay? So that's what we had talked about on Tuesday. Okay, now let's get to these. These are the important ones here to make sure we can do this. Now, on 17, I believe, it actually, when you read this, it says the direction, so this is the important part here today. Sketch the region bounded by the given curves, because on even the homework I give you today, it's some of the regions will be drawn for you, okay, and some won't be. Sketch the region bounded by the given curves. Find the area of this region by evaluating integrals of the form f of x minus g of x dx. Now, what does that mean, f of x minus g of x dx? What were they telling you to do there?
Vertical strips.
Vertical strips. Okay, dx means vertical strips. Okay, because that means your width of this right here, that's your delta x, that the width of that, well, it's going to go to infinity, or it's going to go to 0 because we're going to have infinite strips, infinite rectangles. So when it says to do it in terms of x, dx, that means vertical strips. So then when you got to the next section, it said do those in terms of f of y minus g of y dy. Now we're saying horizontal strips, so understand. Okay? All right, so we want to do vertical strips. Well, that's simply going to be the integral. Top y value is going to be what? Square root of x minus bottom y value, 0 times the width, and it's going to go, the strips are going to fill the space from 0 to 4. Okay? Now, I know you're looking at it, you know, well, that's just a basic area. Sure it is. It's just the integral of the square root of x. Why would you have to put the minus 0? You really wouldn't have to. But I really want to emphasize to you this top minus bottom, top minus bottom, top y value minus bottom y value problem. Okay? All right, and so what do you get for an answer on that one? 16/3. Okay? So that's that area. Okay, now let's jump to number 29. Which number 29, you were supposed to use this same exact region, except now you're supposed to do horizontal strips. Okay, so now you're thinking about a bunch of horizontal rectangles that fill this space and create this area. The integral will add them up, because it's a sigma, right? That's what we learned about the definition of an integral. And it's going to fill them up from 0 to what?
2.
Exactly, because this point right here is the point 4, 2. Okay, you put a 4 in here to square root of x, you get 2. So these strips are going to fill the space from 0 up to 2. Okay, very important difference than what we had here. All right, and then it's going to be this x value minus this x value. What is this x value over here? 4, right? Every time you put a strip on this, its x value is going to be 4 every single time. What's the x value over here? You got to take this equation, square it, solve for x, you get x equals y squared. So of this parabola, this sideways parabola, the x coordinate is y squared. So when I say what is this x, you say y squared. So 4 minus y squared dy. So look at that, totally different looking integral than this one. However, the answer, when you type it in, better be 16/3, right? It's good. Right, you get, it's the same area. So we found it by adding up a bunch of vertical strips, or we found it by adding up a bunch of horizontal strips, same answer. Okay, let's go to 23. 23 said, the region bounded by x equals y squared minus 4. Now, if you want to, on your calculator, you can go, when you go to graph, you can go into relation mode. And you can graph, you can just type in x equals y squared minus 4. You can just type it in like that. You can type in 2x plus 3y equals 17. It doesn't even have to be an x equals or a y equals, right? The relation mode is kind of a cool mode where it doesn't have to be a function, right? Now, if you want to graph it in function mode, you're going to have to solve that for y. Right? If you're not sure what this graph looks like, if you don't remember from last year, it was sideways parabolas, and this would be shifted to the left 4. then if you don't remember that, then, you know, this is gonna be, but you get to use your calculator, so you don't have to remember it and do it by hand necessarily. Okay, so you would add 4 and then square root, and so you get plus or minus square root of x plus 4. Okay, then you can put that into your calculator, and you have to put it in twice. Once is positive square root of x plus 4, one is negative. So that relation mode's a pretty cool thing. Did anybody try that? Did you try that on there? Okay, I think I mentioned it on Tuesday, but if you go into the graph screen, go into relation mode, you can graph these things. Okay, so anyway, get that graph, because you are going to have to be able to graph these and find these regions. And then this is y equals 2 minus x. Oops. Okay, all right. So if we do vertical strips, now if you do vertical strips like you're supposed to do on 23, what do you have to do with this problem? If you're going to do vertical strips, what do you got to do? You got to split it up. You got to split it right here. Okay? Because your vertical strips on this side are going to touch different curves than your vertical strips over here. Here the top y value is on the parabola, the bottom y value is on the parabola. Here the top y value is on the line, and the bottom is on the parabola. You got to split it into 2 parts. Perfectly fine. And so now this y value here is square root of x plus 4. This y value down here is negative square root of x plus 4. Okay, so when you do top minus bottom, you're going to have square root of x plus 4 minus negative square root of x plus 4, which is going to turn into plus. Now you could write that as 2 square root of x plus 4, that'd be fine. And then those strips are going to fill the space from where to where? Negative 4 to 0. The strips will fill that space from negative 4 to 0. I just think that's a good way to think about it. The strips fill the space from negative 4 to 0. So you go ahead and do this. Now, you know, when this book was written, they were planning on you doing most of these by just by fundamental theorem, by hand, right? You may have to do that at some point. Now, on our quiz that we do on Chapter 7, I'm going to let you use calculator in the whole thing. So most of the things we'll be doing in the next couple of weeks will be just typing, get the integral set up, and then you just type it in and get the answer, okay? I don't care about the antiderivative part. Now, in the package, you're going to have some of that, right? You're going to have to keep reviewing and being able to do antiderivatives, because on the final quizzes, that you will have to do that, okay? And now the other part is going to go from 0 to, what is this point over here? Is that 5? 5. So 0 to 5. And then the top y value is going to be 2 minus x. And the bottom y value is negative, so it's going to be minus a negative square root of x plus 4, which ends up being plus. Okay? And whatever, I don't know what that, what is this, number 23? 125 over 6. This says it's 32 over 3, and this says 61 over 6. Those add up to 125 over 6. That sound right? Okay. So, set up your 2 intervals. Okay, so this is clearly one where a horizontal strip would be nicer. Okay, this is x equals y squared minus 4, and this was, what was this, y equals 2 minus x. So if you add the x over there and then subtract the y, you get x equals 2 minus y. So every strip in this region horizontally touches the right side on the line and the left side on the parabola. And so that's good. And they might be saying, well, wait a minute, some of these are touching on the top half of the parabola, some are touching on the bottom half. That actually doesn't matter in this one, right? When you're doing the x-coordinate of this parabola is y squared minus 4 every time. There isn't 2, right? There's 2 y coordinates on this one. There's y equals positive square root of x plus 4, and there's y equals negative square root of x plus 4. Those are different. For this one, it doesn't matter. The top and bottom half of the parabola don't matter. So we got this x coordinate, which would be 2 minus y, and then we're going to subtract the left x coordinate, which would be y squared minus 4. The main thing you got to do is make sure you put parentheses in. So that's the length of this strip. This is the width of the strip. Multiplied together makes the area of the strip. The integral adds up all the strips from where? Way down here, which is what? -3, all the way up here to 2. And you should get, what's this one, 35? 125 over 6. Okay? So on the quiz, when we have our quiz eventually, probably give you a choice. I'll give you a problem like this, and I'll just say, find the area, right? You want to split it into 2 and do vertical strips? Fine. You want to do horizontal strips? Fine. Okay? Most of the time, probably give you a choice. I may ask you to do it a certain way, one of the certain ways, but chances are, most of the time, just which way do you think's better? Okay? All right, so maybe that was easy, but it's an important concept, so I want to make sure we get a handle on it. Okay? All right, so let's go to our packets here, and let's go to sample 3. Let's go to sample 3. So the sub told you, I think, about the 3 things we're going to hand in next Wednesday. So hopefully you've gotten a good start, or mostly finished with most of it. The sample 3, the 2014, and the 2016, those 3. Okay? Now, we'll talk about, there's a few you don't have to do yet on the 14 and the 16, and probably in sample 3. We've talked about a handful of them we're not ready to do yet there. So let's go to sample 3. This is free response number 4 at the back. And the last part, it says set up but do not evaluate, because this was a 9-calculator problem. Set up but do not evaluate an integral expression that gives the area R. Okay? So let's go back and do this if you haven't already. So, very much like the problem we just did. What do you notice in finding the area R? What are you going to have to do? You have to split it right here. Now I kind of made that look like a strip, but it's where I'm splitting. Okay? Now, you might say, well, then do horizontal strips. Well, horizontal strips don't do you any good here either. Because horizontal, I mean, if you think about a horizontal strip right there, you touch the 2 parabolas. Down here, you touch a parabola in the line. And there's even a little bit of, because these meet over here somewhere, there's a little bit of space in here that you can't even see, right? You can't, there's a little bit of area there, and so horizontal strips there would be hard too. So horizontal strips are not the way to go on this one. You just want to split it up, right? So I don't want to give you the impression that, you know, if vertical strips you have to split it up, horizontal strips would be better. You want to split it up. That's not always the case. Okay? So what would we want to do here? We want to do top minus bottom here, and we want to do a top minus bottom over here. Okay? Now I think this was the curve y equals x squared minus 3 over here, and this was y equals x minus 3 squared over here. Now, actually, since they have defined those to be f and g, we could just use f and g, but I'm going to go ahead and write them out anyway. All right? So, what would be an integral expression? So your answer would be you'd want to write the 2 integrals and then put a plus sign in between them, right? So this first set of strips would go from here. What did we find A was? I think we found this one. How much? 1/2. So the integral would go from 1/2. Now we haven't had a lot of integrals that didn't have nice numbers here, but you may have now. I mean, we may get into that now in some of these problems as we go forward. So it's going to go from 1/2 to right there, which would be 2. And it'll be the top curve, which is this one, x squared minus 3, minus the bottom curve, which is this line. And what did we have? We already did this. What was the equation of that line? We did that down in part 2 or B or C, I think.
X minus 13/4.
What was it?
Was it x minus 13/4?
X minus
Yeah, 3/4. So 13/4. Yeah.
13/4. Oh, once you simplified it and stuff. It was a slope of 1, and it was, okay. All right, so y equals x minus 13/4, or whatever version you had that in. So it's going to be this minus the line, which is x minus 13/4. Okay, dx. Now, what if you forget the dx? I think on the AP tests are usually pretty lenient about that. Okay, and then plus And then the integral here would be this parabola, so that's x minus 3 squared minus the line x minus 13/4, right? And like we said, and it said set up, oh, and that was from what to what? From 2 to whatever b was. What was it? 3.5, 7.5. Okay, either way. So that integral goes from 2 to 3.5. Okay, so set up but do not evaluate is something they often do, you know, when it's a no calculator problem, because that's the most important part, right? And then if we're doing a calculator thing, they want an area, then you just type it in. Okay, so top minus bottom, add them up, get the area. All right, let's go to the 2014 packet. This is problem number 2. Now, let's just run through the 2014 packet. Number 1, we can do all parts of that. We should be able to do that. And I'll hand it back, and we'll if there's some you really have some questions about, we can go over. 2, we're going to do part C. That's the only part we can do. We'll have to leave A and B alone. We can do all the parts of 3. We can do all the parts of 4. I think we can do all the parts of 5. And let's see, we said we could not do part C on 6, right? So, and here all you gotta do is sketch in your little curve and then find the slope, and they give you a point and they want the tangent line. And you just do the tangent line. All you have to do is find the slope by plugging into the differential equation. That gives you your slope, you got your point, write your tangent line, and then plug in point 2, right? To approximate point 2. Remember, what the whole point of that is, if you've got a curve and you don't know what the curve is, but if you do a tangent line here at the point 0, 1, well, if you find this point on the line at point 2, it's really close to 0. You find that point, that's really close to the function value at that point. So that's what they're saying. So do the tangent line and then just plug in your point 2. So skip part C. So there's a couple of parts in here we can't do. So let's go back to 2, C. So it says the vertical line x equals k divides R into 2 regions with equal areas. Okay, now it's x equals k, so it's a vertical line. So somewhere right in here, right, is going to be a vertical line that's going to make that be 2 equal areas. Write, but do not solve, an equation involving integral expressions whose solution gives the value k. Well, we did one very similar to this the other day. It had a c in it. Okay, you may remember. So these have to be equal areas. Their integrals have to be equal. So that means the integral from what? From where to where? That'd be this area. Would be the area from 0 to k. And then it'd be what? Well, it'd be top minus bottom. Right? Top minus bottom. What's top minus bottom? That would be, the top would be, this line is y equals 4, so that'd be 4 minus, now, here's where I would definitely use f of x. If I'm doing this one, they've already defined this curve to be f of x. I'm not going to write that all out. I'm just going to go with f of x, especially since I do not have to solve it. It just says set it up. Okay? And that's got to be equal to, so they just said write an equation. An equation just has an equal sign in it, right? The integral from k to, what's this point here? Is it? I don't think so. Oh, this is a calculator one. This is a calculator. Okay, so even though they tell you not to solve it, so what do we need to do? And this happens often on the AP test. You have to find this intersection point, don't you? So how are you going to do that? Nah, not plug in a 4. For y. Yeah, you're going to set this equal to 4. Yeah, you're going to set this equal to 4. Now, actually, it's pretty easy. Actually, we could do this without a calculator, because if you set this equal to 4, it's 2.3, isn't it? Yeah, I mean, I can see it already, because you got this equals 4, and then you subtract the 4, you got 0, you take out an x cubed, you're going to have x minus 2.3 equals 0. So it's going to be 0 or 2.3. So actually, that wasn't too bad. But you could use your calculator. If you didn't notice that, since it is a calculated one, you can do that. So from k to 2.3, and then it's the same thing, isn't it? It's top minus bottom. So it's 4 minus f of x. So it's the same thing. Same minimum. But there you go. That's all they want. That, and then if this was a calculator, or it is a calculator one, if they said to solve, you can just type that in and solve. And that, the reason, so why did they say do not solve, right? Well, number one, they probably had enough points here already to add up to 9 points, so they didn't want to give another point for that, number one. Number two, our calculators, the task calculators, will solve that equation, the other ones won't, right? And so some students taking the AP test won't have calculators that can just solve this equation by typing it in. So they don't want to give that. They try not to give that an advantage to you guys that have those. So that's another reason I think they said do not solve. So anyway, there you go. Okay? All right. So now let's just quickly look at the 2016 packet that I gave you the other day, and let's just talk through that. We should be able to do the first one. The problem number 1, okay, we should be able to do all parts of problem number 2. Now, I've probably given you this hint, and maybe we did this one already. Have we done number 2 already? What's that? Parts of it. Total distance traveled. We talked about that the other day. What's the quickest way to get total distance traveled? Integral of the absolute value of velocity. That is the easiest way to get. Now, it may not be that easy, but since it's a calculator one, and since they give you a velocity equation, then that's an easy way to do it. Okay, now we also talked about how you could take your velocity equation, set it equal to 0, see how many times it stops, and then check its position at all of those. Do the antiderivative. Well, we can't do this antiderivative. That's why that method doesn't work. But sometimes that could work. Do the antiderivative, get position, find where its position is at all the different stopping points, see how far it moved in between them. But this is a really good way to do total distance travel. Okay? So we can do that. Number 3, we can do all parts of that. Number 4, we can't do part C. So this is very much like the one the other day, except or the other packet, except the difference is you're just going to have to go ahead and do those slopes. Maybe we did this already, write the tangent line, they give you a point, you get the slope from up here, write your tangent line, put it in 2.1, and then skip part C. Okay? This one you can't do part B, the volume of the funnel. Okay? That's one of the things we have to learn yet. But the average value of the radius, they give you a radius equation, they want the average value of that. We have a formula for average value of a function. So the average value of that function would be very simple to set that up using that formula. And then this goes back to our old rate of change. What's the rate of change of h? So h prime, they give you r prime, you got h here, so you can do that. So that's just one of those related rate problems from back in chapter 4. And then we should be able to do this as well. Okay? Fundamental theorems, chain rules, stuff like that, plug them down. Okay? So a couple different ones there that we would skip. 5B, 4C. Okay? All right. Now, we do have one little new thing to look at here that's not terribly difficult, and so I'm going to quickly look at that, and I'm going to give you your assignment that you can work on, and then you've got that and finish whatever else you need to for next Wednesday. All right, so what we're going to do here, this is a PowerPoint I borrowed from somebody, Greg Kelly. All right. This is another use, what in chapter 7 remembers about using the integral, right? And again, as an adder, we just use the integral to add up a bunch of areas, the areas of a bunch of strips to get the area of a region. Okay? How else can we use the integral as an adder. Well, what if we wanted to find the length of this curve right here? How far is that around that curve? So if I gave you this on a piece of paper, handed it to you, and said, how long is that? What would you do? What would be some options for how to figure out how long that is?
A piece of string probably.
Yeah, well, yeah, you'd get your book bag or ad, you'd say, hey, you got some string I can borrow? Absolutely. You would throw down a piece of string and you try to fit it around there. Why would that be good? What would that do for you laying a piece of string on it?
You can measure that.
How can you measure that? Straighten it out. The whole point is get it straight. So you put a piece of string on it, then you pull it off and you straighten it so you can measure it. The point is we need to straighten it. To measure a length, it needs to be straight, right? We need to straighten it. So let's just take a little piece of this curve and let's make it straight. And let's call that ds or delta s. S is going to be the length of that red piece. S is the length. So change in s, or the little bit of s, is going to be that. Okay, and so then we can make ourselves a right triangle, and we can let the bottom be change in x, and the top, the vertical component be change in y. And then we could do then we would know that ds by the Pythagorean theorem, okay, would be this right here. So that little red length would be this right here, right? And then, so now that's going to be off, isn't it? Right. That's going to be a little too short, right? So what would make that a more accurate representation? Well, and then imagine, and then I guess I skipped this part. What happened to my, oh, I can't use it. So that would be one little piece. So imagine we did that. Imagine we broke this up into about 5 different pieces like that, right? We measured them. Okay, that would be a little small. It wouldn't be the exact length. How can we make it better? Split it up into 10 little pieces and measure. Or 20. You see where this is going, right? Or 100, or 1,000, or 1,000,000, or infinite number, right? Infinite number. And we would add them up, with a sigma. We would do an infinite, we would add up an infinite number of things. Oh, imagine that. That would be an integral right there. Use the integral to add up. So anytime we can use, we want to add up little things that are smaller and smaller and smaller to give us something, right? Again, this would be what would work. So, let me, why not this? Click. All right, so, all right. So again, we've got this little length here, and if we made that smaller, and we just did little length here and added that up, and then little length here, and then a little piece of length here, and a little piece of length here, if we made those smaller and smaller, eventually we could get that. Okay, so I've just written this out. You don't have to write this out. Just follow along with it. So we said that hypotenuse length is this, delta x squared plus delta y squared. Now, problem is, to turn that into an integral, to turn that into a sigma, I need to have something that is, I need to get, the whole key to any integral formula is you got something here, and then this piece here is really the key. So early on, when we first did integrals, that dx just was sitting there, and it seemed like it had no purpose whatsoever. It was just kind of hanging out there with respect to, but it turns out it's actually the most important thing in the integral, okay? Because this is represented by this represents the thing that is getting smaller and smaller and smaller as we go to infinity. It's the thing that's going to nothing. The width of our strip, for example. So every integral that we create, when we do this by going to infinity, has to have that piece. It has to have a piece that's going to nothing. Well, for us, the piece that's going to nothing, again, could be our delta x, right? The bottom part of that. As we get those 2 points closer and closer and closer, the delta x is going to nothing. So we need to get somehow the delta x out of here and be out, kind of hanging out by itself like this. Okay, so we need some fancy algebra here. So what we're going to do is multiply this by 1. Okay, now, On top, I'm going to multiply by delta x. On the bottom, I'm going to multiply by delta x squared and the square root of that. Why? Because number one, I have a square root here. And number two, I know I want to end up with a delta x out there by itself. Okay, so when I do that, that's going to end up being this. Now let's make sure you're convinced of this. So what happens when I multiply this? Think of a 1, let me put it there. Think of a 1 right here. So now when I put this together, I'll have a square root over a square root. Well, we know if you have square root over square root, that that's just the same as square root of the whole thing. So I have square root over square root, and then I got this delta x just hanging out here. Now, once I have square root of a fraction, I'll have this, and then I'll have my delta x squared down here. Well, then I can split that apart. So I got delta x squared over delta x squared, delta y squared over delta x squared. Okay, so that's what I was doing. That's just some algebra right there is all that is. Okay, now what's delta x squared over delta x squared? 1. We also know that when we have something squared on top and squared on the bottom, that's the same as the whole thing squared, right? That's another algebra thing we know. So I got these two things squared, I can make that just delta y over delta x, quantity squared. And then I got my delta x set down here, which is what I want. Now, what's delta y over delta x? Slope. And remember what we're doing, we're letting delta x go towards 0. So what happens when you do the slope between 2 points, but you let the run go to 0? You got the derivative. You got the derivative. So what we're doing by doing this infinity thing is this is actually going to turn into y prime. Okay, the derivative of the thing, and that's going to be, and then this is s. That's going to be one little strip, but it's going to be one little length that's going smaller and smaller and smaller. We're going to an infinite number. So all we need to add in is the integral to add them up. All we need now is the integral to add them up, and so we get the square root of 1 plus, now this would be y prime, but I'll call it f of x. So f prime squared dx. And then this would just be from point A to point B. So if my strip went here from point A, or whatever, if this is, no, that's not it. If this is A here and this is B over here. So we add up all the strips from A to B, and that we call arc length, or we call that length of curve, either one. And that's just a formula you're going to have to memorize. Okay? I don't think this is ever on the AP test, so this is just a formula you're going, this is one that's probably in Calc 2, possibly. So it's not on our AP test list of things they ask. I don't think I've ever seen it in the packet. But our quiz on chapter 7 will probably have a problem with this. So it's pretty easy, right? The question's going to be, what's the length of this curve? They give you a function from 2 to 4. Well, you do the integral from 2 to 4, you do the derivative of the function, you stick it in there, you make sure and square it, put it inside the square root, type it into your calculator. That's all you have. It couldn't be any easier, right? So if we were doing y equals x squared, so if we wanted to do a parabola, now let me go to the new page. So if we wanted to do y equals x squared, and we want to know how long is this piece right here from 1 to 3, how long is that piece, right? We would just do the integral from 1 to 3, square root of 1 plus what? 2x squared dx. That would be it. That would be it right there. And that would be the length of that. Now, it's important to understand, this is a time that I often like to say this, that if I simplify this a little bit, okay, if I simplified this a little bit, it would be that, right? So we know because of the problem we just did, when we type this into our calculator, it just gives us a number, right? This is a good time to review this idea that a definite integral is just a number, right? A definite integral is just a number. That's all it is. And a number can represent a lot of things, right? Like the number 7 could represent how much money I have on me right now, right? 7 could be how many hours in the school day. 7, right? I mean, 7 could represent a lot of different things. All right, 7 could represent how many teams we destroyed at the track meet yesterday. 7 could represent a lot of different things, right? Okay? And so, same thing with this. This integral, if I just handed you a little half slip of paper with this integral on it and said, what does this represent? Better question would be, what could this possibly represent? Well, what would be the most obvious one that this could represent? What's the first thing we learned about an integral? It's the area under what curve?
That curve.
This whole curve, right? Not that curve, not y equals x squared, but this whole curve, right? I mean, and there's a part in your book, and I think there might be one of the homework questions that asked about this. So that could be just this function. If you would graph it, that would be the area under it from 1 to 3, right? We also just saw that this integral represents the length of that curve from 1 to 3. Okay, now if they ask you on the homework, they say, what curve, like to go backwards, what curve was this the length of? You'd have to unpack this, wouldn't you? You'd have to say, oh, okay, well, what would that be squared? Well, that'd be 2x quantity squared, and what function would have a derivative that was 2x? Oh, that'd be x squared, right? You kind of have to unpack that going backwards. So not a big deal, but just understand that an integral is just a number, okay? This integral happens to be the length of that piece of the curve. But it also can be the area under that integrand right there. Okay, so next line of your packet, there's a few in the book. Those are the arc length ones. Okay, so there's a few in the book. So it's the next, there's 2 lines actually. And that LH packet I gave you, that LH packet is some areas. Those are just areas between. So those are some right minus left, right, top minus bottom, right minus left kind of practice. Okay, so that's homework for Wednesday, and then of course that packet work that hopefully you got a lot of that done yesterday, but you know, while I'm here working on Monday and on Tuesday, and you guys are sitting home, well, not all of you, some of you will be here for the ACT. All right, go ahead and work the rest of the time.
I didn't hear where you're going. I didn't get the
We also need the LH. Thank you guys.
No, I haven't.
Yeah, the one, chapter 7. Chapter 7 is another one.
When did you get that application?
Tuesday.
Yeah, I was here today. Thank you.